So it's my pleasure to introduce Michael Hermele, who is going to tell us today about some amazing discoveries in the physics of fractons, of which some of you may have heard from last week's colloquium. So let me say a few words about Mike. Mike did his undergrad at Harvard before joining UC Santa Barbara, where he worked with Matthew Fisher on his PhD. Mike, I do not recall the title of your thesis. You'll have to tell us in a moment. And after having done that, Mike has moved to MIT, a couple of years doing a postdoc there. And then in 2007 became a faculty at University of Colorado at Boulder, where he's been since. So Mike is known for several major accomplishments. One of them is going back to his PhD work, which is related to the discovery of U1 quantum spin liquids and their relationship to the possible effects in what's known as magnetic, so it's a pyrochlore frustrated magnets. And then more recently, he's been widely known for his work on classifying the symmetry protected as well as so-called symmetry enriched topological phases. And more recently, he's done much work on the Fracton phases of matter, which you will hear today. Mike is the recipient of several major awards. He's won both the DOE Early Career Packard Fellowship. He's a fellow of the American Physical Society, and he's investigator of the Simons Center, I think being part of what's known as ultra quantum matter. Is that the correct title?
Yeah, it's a Simons collaboration. Yeah, it's the Simons collaboration on ultra quantum matter.
All right, so here we go. So today we'll hear an excerpt of what ultra probably means, right? Because apparently fractons is part of that, of the thrust of that ultra quantum matter. And so without further ado, I give it to you, Mike.
Okay, thanks very much, Andre, for the really nice introduction. I think my thesis title was Quantum Critical Phases in 2 and 3 Dimensions, but I'm not going to be talking about that today. The other thing I can say about my PhD time is that actually Matt Foster was one of my office mates. Yeah, so Matt and I go way back. All right, so as Andre said, I want to talk about some aspects of what are called fracton phases. And what I'm going to start by giving an introduction to fractons, just a sort of general introduction, give you a feeling of what they are. And then what I want to emphasize is kind of the interplay between fracton phases and quantum field theory. And so the purpose of the talk is really not to tell you about a specific piece of work, although some specific pieces of work, actually, I think almost all by other people, will show up along the way. But the point is really more to give a perspective on what I think some of the interesting questions are in this topic, and sort of give a flavor of one reason, in my opinion, one of the important reasons why people think this is an exciting and important topic. Okay. And it's probably the reason, which is hardest to read anything coherent about in the literature. So maybe that's a good reason to talk about it. And partly because of that, actually, Xie Chen and I are working on trying to write up some of this into a perspective article. But so far, there's nothing to read. There's just this talk. So as I said, I'm going to start with an intro to fracton phases. And then next, I need to, before I tell you kind of how fracton phases relate to quantum field theory, I need to say a little bit about how the relationship between quantum phases of matter and quantum field theory usually works in more familiar examples. And then I'll explain I'll give some discussion of how and why fracton phases are beyond that, and maybe comment on what that might mean. Okay, so I want to start. So I want to introduce fractons, but I want to start with a little bit of a warm up and first introduce the toric code model, because the concrete models for fractons that I'm going to write down are very similar to the toric code. They're slightly less familiar, and they're in 3 dimensions instead of in 2 dimensions, so it's harder to draw pictures. Okay, so the toric code is just an exactly solvable spin model in 2 dimensions, and it it goes back to Kitaev in 1997, although really it's just another version of Z2 lattice gauge theory, which actually goes back much farther to Wegener in the 70s. Okay, so how do we write down the toric code? Well, there are different versions of it, but this is a version on the square lattice, and on every link or every edge of the square lattice, we put a single qubit, and we'll write the Pauli operators of these qubits as x's and z's. So x on the link L, that would be like a sigma x Pauli matrix. Z on the link L, that would be like a sigma z Pauli matrix. Okay, and here's the Hamiltonian. It's a sum of two kinds of terms. And the terms all commute with one another. So the first kind of term, it involves a sum over vertices. And for each vertex V, you have this AV operator, and it's just a product of the Pauli Z operators over this red cross, which that comprises 4 links. Okay, and the other term, so often we'll call that a vertex term. The other term is a sum over these square plaquettes. And the operator there is BP, and it's just a product of Pauli X operators going around the perimeter of the plaquette. So it's easy to check that these commute with one another, and so that implies that in a ground state, all the AVs and all the BPs have eigenvalue 1. Okay. All right, and there are 2 kinds of excitations. So you can violate these ground state constraints. You can think of them as constraints. You can have an excitation where AV is -1, and often people call that an E particle because it's like the electric charge of a Z2 gauge theory. Or you can have a plaquette where BP is -1, and that's often called an M particle, and you should think about a magnetic flux of a Z2 gauge theory. Okay, but I don't really need to explain the connection to the gauge theory language here because we're not going to use it, but I'm just mentioning it for some context. So let's say a little bit about the properties of this model, which we're going to shortly contrast with some properties of Fracton phases. So one thing you can do is if you act, let's say, on this link with the X operator, then you create a pair of E particles at the 2 endpoints of this link. And once you've created this pair of E particles, you can act with more X operators, say here, 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 and here, and you can separate these E particles from one another. Okay? You can separate them as far as you like. And you can, E particle that's moving here, you can think of this one as having moved along this blue path. You can move it around any way you want. So why are these excitations interesting? Well, they're fractional excitations in the sense that they're not locally creatable. There's no way to make a single E particle by any local process. And same thing for an M particle. And going along with their fractional nature, these excitations have some non-trivial statistics. So E and M, they're bosons in terms of their self-statistics, so there's nothing funny there, but they have mutual braiding statistics. And if you have an E, which for example is just sitting still, and you take an M and you cycle the M around the E, if the M makes a full circle around the E, then the system picks up a statistical phase of pi or -1. Okay, so there's some, you can think of there's some kind of Aronoff-Bohm type interaction between the E's and the M's. Okay, just like you would expect if the E is charge and the M is flux. Okay, so so that's one reason that these excitations are interesting. You can also ask about the ground state physics of this model, which is non-trivial. And one way to see that is to consider a system with periodic boundary conditions, which topologically is a torus. And on a torus, there are 4 degenerate ground states. And you can think about these 4 degenerate ground states as just 4 different ways of threading a Z2 flux through the 2 different cycles of the torus. So you can either thread no flux, thread flux through one cycle, thread it through the other, or thread it through both. And the interesting property about these ground states is that they're locally indistinguishable. So there's no way in the limit of a large system to tell these 4 ground states apart. Okay, and that has a number of consequences. One thing it means is that the degeneracy of these ground states is robust. So the toric code model is very special and exactly solvable, but you can add arbitrary perturbations to it, not worrying about any symmetries. And no matter what you do, as long as your perturbation is not so big that it closes the gap to bulk excitations, these 4 ground states have to remain degenerate. And it's precisely because they're locally indistinguishable, right? The way that you would be able to split them by adding local perturbations is if there was some way in which you could even tell the difference between these states locally. Okay. Another reason that this is an interesting property is that this ground state space, this 4-dimensional space of ground states, it has desirable features if you might want to use it to store quantum information, right? Precisely because you can't tell the ground states apart locally, it means that you can't disturb quantum information that you store in that space with local measurements. And so, you know, that's the starting point of a lot of interesting ideas in quantum information, okay, which we may come back to a little bit. Okay, so that's just kind of background and a bit of a warm up. So what are fracton phases, right? I'm going to write down models for fractons that are similar to the toric code model in just a minute. But backing up a little bit, you know, more generally, what are fracton phases? Well, they are quantum phases of matter, 0 temperature phases of matter that have gapped excitations of restricted mobility. And so here's an attempt to illustrate that in pictures. So this is some point-like excitation, and the oval just shows where it sits in space. And the idea is that there's no local process by which you can take this excitation and move it to the right side of the oval, okay? However, it's not just that this excitation is completely immobile, but it has a more interesting kind of cooperative kind of mobility. So you could destroy this excitation here at this corner of a square, and you could move it there, but you also have to create 2 other excitations of the same type at the other corners of the square, for example. Okay, so if you know this kind of mobility is allowed, this is not, it still means that if you have a single isolated fracton, and you have energy conserving dynamics, it's not going to be able to move. The only way for it to move will be to create more excitations. So a single one of these is going to be stuck. Okay, the mobility is restricted. And it's really very stuck. So you might think of other things in condensed matter physics where excitations are stuck. The most familiar is probably Anderson localization, right? In non-interacting systems where you have localized wave functions. But this is very different from that, because here, what's going on is that there's really no local process at all by which you can move, just destroy one of these excitations over here and create it somewhere else. In an Anderson localized system, it's different. If you're willing to violate energy conservation, you can take a localized wave function at one point and you can move it somewhere else, and that's fine. There's a process which you can think of as local, meaning that you just do stuff in the region along which you're moving the excitation. You'll be able to move the excitation. So this is it's a different kind of it's a really new kind of restricted mobility from other phenomena that we've known about for longer. Okay, so, you know, there are other ways to restrict the mobility of an excitation than just having it completely stuck. You can have excitations that are constrained to move along lines or in planes in a 2-dimensional system. So these excitations moving along lines are called linons, and the ones moving in planes are often called planons in this business. But fractons is the term that I'll reserve for the excitations that are completely immobile. Okay, so this is sort of a definition of fracton phases. These are phases that have these kind of gapped excitations above the ground state. Now, as far as we know, this phenomenon is something that, you know, with maybe some minor caveats, this is basically a phenomenon that's limited to 3 dimensions. Okay, so, and certainly for fracton phases where all the excitations are gapped, in terms of all the examples that we know are in 3 dimensions or perhaps higher, but we'll focus. So we're going to focus on 3-dimensional examples for this talk. So here's a model very much like the toric code where this phenomenon happens. So this model was discovered by Vijay, Ha, and Fu in 2016. And there was earlier work on fractons that I won't have a chance to talk about. Well, I may mention some of it, but this work really kicked off a lot of interest in fractons among condensed matter physicists, because this was sort of the moment when people realized that there actually are reasonably simple models for this kind of phenomenon. Okay, so how is this model constructed? Well, like the toric code, we place qubits on the links of a 3-dimensional simple cubic lattice. There's also a three-dimensional version of the toric code, of course, but this is not that model. It's a different model. And the Hamiltonian is, again, a sum of two terms. Okay, there's one term which is a sum over cubes, and we take a product over Pauli X operators on every link of the cube, and then we sum over cubes. That's why this is called the X cube model, because of this operator that shows up in the Hamiltonian. Okay, so that's one term. Another term, we sum over vertices, and on each vertex, we have something that looks exactly like the vertex term of the 2D toric code. So we have products of Z operators over sets of 4 links. So this is a set of 4 links that lies in the XY plane, and then you also have these in the XZ and YZ planes. So there are 3 different orientations of this term. And again, you can check that these terms all commute. They have eigenvalues plus or minus 1. So in the way that you would solve this model and compute anything about it you want is just like for the toric code. And just like in the toric code, there's a gap to local excitations. Okay, so okay, so what about the ground states of this model? I'll talk about the ground states, then I'll talk about the excitations. So I told you that in the toric code model, there's a ground state degeneracy of 4 with periodic boundary conditions. So here something funny happens. There's actually a large ground state degeneracy with periodic boundary conditions. So if you have a L by L by L system and periodic boundary conditions, the log base 2 of the ground state degeneracy actually grows with the linear system size, and precisely it's 6L minus 3. So the ground state degeneracy grows exponentially in L, and this is what we call a subextensive degeneracy. Okay, it doesn't grow exponentially in the volume. That would be an extensive degeneracy, but it's a big degeneracy. And now whenever you see a big degeneracy like this, your first reaction should be like, well, surely if you start adding some generic perturbations, you will split this degeneracy. But remarkably, that doesn't happen here, just like in the toric code, even though here there are a lot more ground states. And the reason is the same as the reason in the toric code. So just like in the toric code, this large number of ground states, they're all locally indistinguishable. And so the ground state degeneracy is similarly robust as in the toric code. It's really as robust. It doesn't rely on any symmetry properties or anything like that. Okay, so this is often what this property of this robust ground state degeneracy is often referred to as topological order, going back to work of Wen in the 90s. Okay, so so this is weird and kind of surprising. Now, I mean, one thing that's worth mentioning is there is a trivial way to get this. Yeah, go ahead, Caden.
So when I think about topological order shouldn't know anything about the manifold except the topology, but this has a degeneracy that depends on L. So is there a tension there, or?
Well, yeah, right. So usually we don't actually use the term topological order for this anymore. I mean, the tension is only about the terminology, really. So in Wen's early work on topological order, he really defined topological order as this property of having these locally indistinguishable degenerate ground states on a space like the torus. And so that is still true here. So it's definitely true that these models have topological order in the sense that Wen originally meant it. Now, as time passed, that term also became associated with other things like having a description in terms of topological quantum field theory, which we do not have here. And so that's something that we'll be getting to. So it's not really proper to call this, I wouldn't call this a topological phase, because for me, topological phase is something that has a TQFT description, but not everybody has the same terminology there either. Yeah. Yeah, okay, good. But it's certainly true that this physics shares, it shares certain things in common with more familiar topologically ordered phases, although there are other things that are very different. Yeah. Okay, so let's talk about the excitations. I said something about the ground states. What about excitations? So there are 2 kinds of excitations, right? There are 2 terms in the Hamiltonian. You can violate either one of those constraints. There are cube excitations where you make BC equals -1. And the way that you create these is you act somewhere with Z and you create a neighboring group of 4 of these cube excitations, like these green shaded cubes here. There are also excitations that live on vertices. That's where you violate the other term in the Hamiltonian. And to create those, you act on some link with X, and you create two excitations at opposite ends of that link. Oh, and let me jump back. There's something I forgot to say, which is kind of an important point. Back to ground states. One thing to mention about this ground state degeneracy is that there's kind of a dumb way to get a ground state degeneracy like this in 3 dimensions. You just stack up a bunch of 2D toric codes, say. And so one thing you have to do in thinking about the X-cube model and other similar models is convince yourself that the model is not somehow secretly a stack of toric codes or something like that. So already a hint of this is provided by this -3. If it were not for the -3, this would be exactly something you can get as a stack of toric codes. But with the -3, it's very hard to understand. But you can also make more detailed arguments. And there's really a sense in which you can prove that this model is not just a stack of toric codes. But it's kind of important for context. There's a sense in which something like a stack of toric codes actually is sort of a fracton phase, but it's like a trivial example of a fracton phase. Just knowing that example for many, many years did not lead people to think in this direction and discover the other non-trivial examples. Okay, so what about let's talk about the line-on excitations first, okay, of these two types of excitations. So because you can create them at opposite ends of a link, you can keep doing that and you can separate them as far as you want, so two of them can move along a straight line. The interesting thing is that if you take one of these excitations and you want it to turn a corner and go in another direction, it turns out that you can't do that without leaving another excitation behind at the corner. So you actually leave another excitation behind at this corner, and this excitation would be able to move along the line that's perpendicular to the page. Okay, so that restricts the mobility of the line-ons. They can move in lines, but they have trouble turning corners. Okay. Now, what about the fracton excitations? So these cube excitations, they are fractons. So how to get a feeling for that? So suppose we act with a Z operator somewhere. We make these 4 excitations. Well, you can act with Z again, and you can separate these 2 pairs of excitations from one another. And then you can act with Z some more times, and you separate all 4 of these cubes from one another. And you keep doing that. And what you see is that you can create isolated cubes at the corners of this kind of rectangular membrane. All I mean by that is this is just some rectangular region, and there's an operator defined on that region, which you just construct by taking a product of Z through every link that cuts through this membrane. And you create isolated fractons at the corners. Okay, and you can convince yourself, I mean, at least intuitively from staring at pictures like this for a while, that you're not going to be able to move an isolated fracton without creating other fractons. And you can, all these statements can be proved in more rigor, but my purpose here is not to really give you the rigorous arguments for anything, but just to give some intuition. Okay. So these cube excitations are immobile fractons. So that's pretty much what I want to say about the X-cube model. We'll come back to it a little later in the talk. So I want to give you an example of a different kind of fracton model, which is actually quite a bit more complicated, but it was discovered earlier. So this is a model that was discovered by Ha as part of his PhD thesis in 2011. And he called it the cubic code, and now it's either called the cubic code still, or it's called Ha's code. I guess here I'm calling it Ha's cubic code. I think I should mention, I didn't put it in the talk, but just a quick comment on history. This was not the first work on fractons. The first work on fractons was actually by Claudio Schamon in 2005/2006. So Schamon actually wrote down the first model, discovered the first model that has fracton excitations in it. As far as anybody who's worked on this subject knows. Maybe there's something else in the prehistory where we didn't notice that, but he didn't just write down the model. He also recognized that its excitations were fractons. And he was kind of interested in models that have slow in quantum models that have slow glassy dynamics and have a hard time equilibrating. And you can sort of imagine that that's going to be one of the phenomena in models like this, because if you have a bunch of these excitations, it's hard for them to move around. And that's what he was mainly interested in. And that's actually still one of the themes that runs through this subject, and one of the kind of dominant threads of work and questions that people are thinking about. His work was kind of ignored for a while. Well, there are some interesting anecdotes to tell about that, but let me not dwell on this for a reason. There was no good reason to ignore his work, but it was ignored anyway. But the subject got some new life when Ha made this discovery in 2011. Although I think myself and a lot of other people still didn't pay that much attention, because it just seemed like Ha's model was so complicated and it was hard to get a handle on it. And I still feel that way about Ha's model, actually. It's pretty hard to get a handle on. So what is the model? It's easy enough to write down. It has spins on the vertices of the cubic lattice, except there are 2 qubits on every vertex. And it's built out, the Hamiltonian is a sum of 2 commuting terms, which are just products of Pauli operators. So it's like the toric code in the X-cube model in that way. I'm not going to explain it in as much detail as the X-cube model, but I'll just tell you that all of the non-trivial point-like excitations of this model turn out to be immobile fractons. In the X-cube model, there are fractons and there are linons. It's also true that if you put 2 fractons together, that thing can move around. In this model, either an excitation is something boring that you can make locally, or it's a fracton. It turns out that it's very hard to create well-separated fractons. There are actually logarithmic energy barriers to do that. So if you want to have a process where you make a bunch of fractons and separate them, in this model, there's an energy barrier to do that, which grows with the desired separation size. And on the next slide, I'll give you a feeling for why. So how do you make excitations in Ha's code? Well, there's one class of excitations that you can create in groups of 4 that live at the corners of a tetrahedron that looks like this. Okay, and so that's a group of 4 excitations that you can make locally. The question, you can sort of view that as an elementary process that you can do. And the question is, how do you put these processes together as a building block to separate these excitations far apart? So I won't try to draw that in 3 dimensions because it's a little hard, but I'll draw a 2D cartoon using triangles instead of tetrahedras that gives you exactly the same intuition. So imagine that we had a model where you could create 3 excitations at the corners of a triangle. Okay, and imagine these are Ising-like excitations. So if you put the 2 of them together, that's like having no excitation. A way to make 3 excitations at the corners of a bigger triangle would be to act with 3 operators like this, right? You're acting with an operator which you can think of as the shaded triangle creates these 3 excitations. So then you can act with 3 operators at vertices like this, and like this, and like this. You'll create 2 excitations and they'll cancel out. But at the outer vertices of this big triangle, there will still be these point-like excitations. And so this is a way that you can make 3 of these excitations farther apart. But then you see that you can keep putting this building block together, okay? And here it is again, you create these 3 excitations even farther apart. But what we're doing here is we're just constructing a kind of fractal called a Sierpinski fractal. And so in order to create 3 of these well-separated excitations, you need an operator where you act with a product of some Pauli over a fractal region. Okay, so it will have holes in it and it will be some complicated shape. And so the excitations are created at the corners of these fractal regions, and it makes it pretty hard for them to move around. I didn't try to draw a picture of this in 3 dimensions, but in 3 dimensions, it's another kind of Sierpinski fractal, which is actually a tetrahedron. And this is an image that I found using Google, which is apparently a sculpture in a park somewhere in Minnesota of a Sierpinski fractal. I've never been there. I did not take the picture myself. Okay. So this is very different from what happens in the X-cube model, right? The X-cube model, the way that you make fractons that are far apart is you act with membrane operators, which are 2D objects, but here you have these fractal objects, which are much more complicated. So it's really hard to move the excitations around in Ha's code. Yeah, okay. Okay, good. Yeah, there's more that I could say about that, but I think I want to kind of move on to the next part of the talk. So, just to kind of summarize all this, I gave you a bit of an introduction about, what Fracton phases are, and I showed you a couple simple theoretical models for them. So, there are lots of questions that one could ask at this point, but maybe the main one that I should say something about is, why do we care about these things? So why is this an interesting topic? Why is it an important topic? So there are a lot of different reasons. So the first one, for condensed matter physicists is maybe it's almost a self-evident reason, is just that this is a new and still quite poorly understood class of quantum phases of matter. So they're really very different from even, modern examples of topological phases that we've understood over the past, say, 10 or 20 years, in many cases now reasonably well. So another reason, also kind of a good condensed matter-ish reason to be interested in these subjects, in this subject, it actually goes back to the original work of Shimon that I mentioned, and these are systems with interesting constrained non-equilibrium dynamics. Right? If you imagine that you make a bunch of fractons at finite density, and then you let the system evolve under quantum dynamics, either as a closed system or maybe coupled to a bath, the individual fractons can't move, but if you are at finite density, they can move in some more interesting cooperative ways. And so you might imagine that the quantum dynamics of such systems is going to be interesting. And indeed, indeed it is. So that's something people are still actively thinking about. It's kind of typified by slow relaxation to thermal equilibrium. That's one of the main phenomena. And this property is actually related to the next reason to be interested in fracton phases, which goes back to the work of Ha. That was one of the main motivations for Ha and other people more in the quantum information community to start thinking about this topic, is that some of these fracton systems have desirable properties as quantum memories, right? So I mentioned that you can try to store quantum information in the ground states of the toric code model. And the toric code has some desirable properties for doing that, but it's not perfect. And if you really wanted to use a toric code as a quantum memory, you'd need to do some kind of active error correction. If in a non-ideal system where your memory is coupled to some finite temperature bath, and you have to worry about errors from the bath. And the reason that you still have to do active error correction is that basically if you're sitting in a ground state of the toric code, and you have a thermal excitation where you create a couple of these, say, E particles, what can happen is the E particles can zip around the system and then annihilate on the other side and go back into the ground state, but actually you go back into a different ground state. So you wind up with matrix elements that will take you from one ground state to another. Now, if you quickly go in and you locally correct that error before the E particles can fly away, then it's not a problem. But once they start to wander far apart from one another, even if they never actually meet and annihilate, you have a big problem because it's very hard to tell what ground state your error state came from. And you can think of the kind of fundamental problem is that there's no energy barrier that keeps you from pulling the E particles farther and farther apart. Once you make them, you pay some finite amount of energy and then they can move wherever they want. And that's actually very bad for storing quantum information. With error correction, it's okay. But what you really might want, ideally, is to have
Mike,
a
can I
quantum
ask a
memory.
question? Just to
Yeah, go
make
ahead,
sure that
Kate.
I understand that toric code case. So you do have to do the error correction, but the time scale should get exponentially long in the system size, or is the temperatures lowered or something like that? Is that right? Or
no, I don't know. The time scale is actually constant with respect to the system size. I think it does get exponentially longer as you lower the temperature.
okay, so I guess I was thinking that the sort of gas of these E particles must be exponentially dilute, but I guess the point is you only need one of them to screw up your
right. You don't need a lot of these excitations, and the point is that, like, if you create a couple of E particles locally, all they have to do is start wandering some large distance, but they'll just diffuse, and there's no energy barrier to doing that. And they don't actually have, if the problem occurred only if they actually came back together and met again, then you might be okay, because there's, the chance of that happening is relatively small. It's going to be smaller in a larger system, but they don't actually have to meet to cause a problem. All they have to do is wander a distance on the order of the system size. But that will happen, you start out with a completely localized particle, it's gonna wander that distance pretty quickly. And so, I'm not enough of an expert to tell you how that actually translates into a constant memory time that just goes to a constant as a function of system size, but that is the result anyway. So so
it's a constant memory time, but the constant gets exponentially longer as temperature is lower.
Yeah, if you lower the temperature, then the constant still gets bigger. Yeah. Right. So what people really want in that field, at least theoretically, is to have something called a self-correcting quantum memory, where basically the system's own dynamics kind of takes care of the error correction for you. You don't have to do any active error correction. And Haas code model turns out to be not quite that, but it's the farthest step in that direction that we know how to go in a three-dimensional system. So the reason is that you can create these Fracton excitations locally, but it's hard to separate them because there are logarithmic energy barriers to pull them apart. You might think that's good enough, but for entropic reasons, it turns out that for very large system sizes, the memory time still goes to a constant, but it performs better. It increases as a power of the system size before it goes to a constant at some large system size. So that's another reason to be interested in this subject. And there's a lot more to say about that. Okay, I could have given the whole second half of the talk about that. It's not something I've thought about as much, but it's a really interesting topic. So what I'm going to focus on is the last thing, is that Fracton phases really raise some very challenging issues about the role of quantum field theory in understanding quantum matter, which are probably not limited in the end to Fracton phases themselves. So maybe we can learn some more general lessons from studying this topic. And at least for me, it's because of this that that I also find the first reason here particularly interesting, because the relationship between Fracton phases and quantum field theory seems to be so different from other phases that I already know how to understand better. I would really kind of emphasize that these are really new and they're really poorly understood. It's not just some other new class, we've encountered many different new classes of phases over the past 10, 20 years, but some of them are more new than others. And I think this one is really new. It really forces us to go beyond our existing ways of thinking. And we're still, I think, actually very far from figuring out how to do that. Okay. So before I tell you about that, I want to sort of give you a brief account of how I think we usually do things. So you could call this a standard paradigm for quantum phases of matter and quantum field theory. Okay, so one of the kind of major problems in quantum many-body physics is to understand quantum phases of matter. So here we're always at zero temperature. And the rough definition is that phases are some kind of deformation classes of quantum systems. Okay, so you vary parameters, you have these connected components of parameter space, those are your phases. There's another thing that goes along with this, which is that usually when you define phases, you also want to allow yourself to stack with some kind of trivial system. The most physical thing you can have in mind there is like, you have some electronic solid that you'd like to model. A lot of the time we like to use lattice models, but that's an idealization. And really there are always core levels that we'd like to ignore. And throwing away the core levels is an idealization, and you can choose to keep some of them or keep none of them, or you can make different choices and you'll get different models. But what phase you're in shouldn't really depend on that choice you made as a theorist for what model to write down. And the way that you can handle this is to say that, like, well, there's some trivial stuff. We can have our ground state wave function and we can stack it with stuff that maybe we ignored at some level of description. Now we want to put it back in our description. So that's another important ingredient, not mentioned as often, that comes into the definition of phases.
So
Okay.
here you're allowing any type of deformation as opposed to constraining with the symmetry or something, or
Either way, so you could, yeah, it's just different problems. So you could say that you have some symmetry that you imposed, and then you're only going to be able to, you only, these G1 and G2, they might be parameters that respect some symmetries, or you might have a system where no symmetries are imposed, and then you don't have that restriction. Usually you'd have a restriction of some kind of locality, at least, like finite range interactions or interactions that, decay no more slowly than some power law or something like that. Usually I have in mind finite range systems. Yeah. So, and, and in phases, what do we care about? Well, we usually care about, what we call universal properties, which you can think of as just properties that are the same everywhere in the phase, things that don't change, or maybe they change in a simple way parameterized by a few simple quantities. So what are examples? Well, long range symmetry breaking order, right? Like the, order in a ferromagnet. Topological order, like properties of the toric code that I told you about, the braiding properties of its excitations or its ground state degeneracy. Related to that, in quantum Hall liquids, you have quantized Hall conductivity. So these are all universal properties of some phases. And so one thing that we often want is a theory that keeps track of the universal properties and throws away other stuff. Okay, it usually that's a good way to try to simplify things. We don't care usually about every detail of some lattice model that we start with. We're mainly interested in universal properties of a phase. Okay. And a way to, the kind of main conceptual tool that lets us do this is the renormalization group, which here I really mean, of course, renormalization group means a lot of things as well. There are also a lot of technical tools that are part of it. But here I really mean RG as a conceptual tool. So I'm not thinking about any particular RG scheme or anything like that. Although sometimes you need to, zoom in and get into those details in order to say anything precise. But for these purposes, I don't need to. And so RG, you can think of as a way of focusing on the physics at longer and longer distances or times, and at the same time getting rid of short distance degrees of freedom. So the idea is kind of universal properties have to do with the physics at long distances. And so if you've set up any RG scheme properly, it should preserve universal properties in a phase. Okay, and of course, if you keep doing this, you're getting rid of short distance degrees of freedom, you're kind of coarse graining your lattice structure, and you imagine that this might lead you to some continuum description. And so indeed, RG you can think of as a kind of link between a lattice model description and some effective quantum field theory description that lives in the continuum. Okay, and so here's an example that's hopefully familiar to everybody where this works really well. We know a lot about this example. So it's just a quantumizing model, which I've drawn in 2D, but it doesn't have to be in 2D, right? So we just have spins on, say, a square lattice. They have a ferromagnetic Ising exchange and a transverse field. And of course, if you tune the ratio of those two terms, you have a ferromagnetic phase, a paramagnetic phase, and a critical point between them. So that's the phase diagram. And we know how to write down a field theory for this. It's just phi to the fourth theory. So, and the idea is that the field phi is just a coarse grained version of the Ising spin, sigma z, of course. And you can describe the critical point and the two phases in this field theory. So all the universal properties of this model, both its phases and its critical point, are encoded within this field theory. Okay. Now, an important point about this description is that this phi to the fourth theory, if you think about it carefully, it lives in the continuum, and that's nice, but it still includes some non-universal information. In particular, if you want to calculate anything with this theory, you have to put in a cutoff somehow. And there are a lot of different ways of doing that. and there's nothing special about different ways. And so the physics at the scale of the cutoff is very much non-universal. It will be different than this Ising lattice model that you started with, but it'll be some other non-universal physics. So just having a continuum theory is not really what we're after, because continuum theories can come with their own non-universal baggage. But the thing that we can say, which which this Lagrangian does not really encode, is that here, at least at the critical point, there is a kind of theory that you might call a scaling limit theory that only retains the universal information and it throws out everything else. And so that's a conformal field theory for the critical point, which we understand in great detail if this were the 1D quantumizing model, and we understand a reasonable amount about it in the 2D Ising model. Okay, this is some more abstract description that doesn't really rely on a Lagrangian, but it does keep track of things like critical exponents and so on. Okay, so that's one example. But to bring things a little bit, but that example is a little bit far from the world of Fracton physics because the critical point is gapless. So let's get back a little closer to that. So let me talk about the toric code model. So there's an important sense in which the toric code model is an RG fixed point. Even the lattice model is an RG fixed point. It's a very special property of the lattice model, but this helps us to understand some of its physics. And so this is something that often goes under the name of entanglement RG. It's a way of doing some kind of an RG on commuting Pauli Hamiltonians like the toric code. So you start with the toric code on an L by L system, and then you act on this with some unitary operator, which has some nice locality properties. And what you do is you take your toric code ground state and you convert it into a product of a toric code ground state, but on a smaller system where the linear size is half what you started with. And that new ground state is producted with just a bunch of spins that are up, just a trivial product of up spins. So these are some trivial degrees of freedom. Then we can say, well, these decoupled spins, they're pretty trivial, so let's just integrate them out. We eliminate them. This is often a step in the RG. We throw away some degrees of freedom. And once you do that, then you say like, okay, now we're left with a toric code model on a system size, which is L over 2. Now, if you imagine taking the limit where you're doing this in infinite space, you haven't actually changed anything. And so you would say, okay, the toric code is going into itself under one step of this RG. So it's a kind of fixed point. And it relies on eliminating these degrees of freedom that we consider trivial. Okay. Now, and going along with that, there are various continuum field theories that describe the physics of the toric code. So I wrote down a Lagrangian for one. We're not going to do anything with it, so I don't really need to explain it. I just wrote it down just to show that there is a Lagrangian that you can write down. It's a kind of very honest field theory, doesn't rely on anything very abstract. It's just a kind of Chern-Simons theory. And this encodes all the universal properties of the toric code phase, like its ground state degeneracy, the fractional excitations, their braiding statistics, and so on. Is this a scaling limit theory in the sense that it only encodes universal properties? It's a little bit of a delicate question to answer for these Chern-Simons theories. I think probably not quite. You can certainly perturb this theory in various ways where it looks like it will include some non-universal information. There are theories that are definitely scaling limit theories that only include the universal information, but they're more abstract. There are more abstract formulations of TQFT where you don't even write down a Lagrangian. Okay, and then it's clear that you're only keeping track of a universal information, sort of by construction. Okay, so so that's kind of quantum field theory for the toric code in one slide. So to kind of back up and synthesize all of this a little bit, there's a nice picture you can draw. And the kind of key idea here is that phases we associate with stable RG fixed points, right? You imagine that the idea is you kind of keep coarse graining within a phase, and eventually you might flow at longer and longer distances to some kind of ideal exemplar of that phase, which is the fixed point, where you just sit there in parameter space. Sometimes, there are some caveats about that statement, but let me avoid them if nobody asks. going along with that, we expect there to be some continuum effective quantum field theory that encodes all the universal properties. And at least sometimes, like in the examples I gave, we can find a scaling limit theory where that quantum field theory really just encodes the universal properties. It doesn't, we've kind of just distilled the physics of a given phase down to its essence. Okay, we don't, need to worry about what's going on at the cutoff scale or something like that. Okay. And one part of this is some old conventional wisdom, which is that for gapped phases, the scaling limit theory is a TQFT, topological quantum field theory. Okay, which I didn't define in general, but I gave you an example at least in this Chern-Simons theory. But fracton phases actually show us that this conventional wisdom is just wrong.
Mike, before
yeah.
going to the fractons, so
Yeah.
maybe I'm misremembering, but I thought at some point Xiaogang Wen was making a big deal that these SPT phases were also not scaling limits of TQFTs. You had to do a lattice QFT or something. Maybe I'm just misremembering, or maybe we should talk about it.
He did. He was emphasizing that point for a while. I don't think that's correct. There are continuum formulations. I mean, although I also don't think that Xiaogang was saying anything wrong. I think he probably had something slightly different in mind when he was making those statements. But there are definitely continuum formulations of, well, for every known SPT phase. In fact, those field theories have been classified and it's understood pretty systematically now. But I mean, it's true that, yeah, in some of the early work on SPTs, there's a space-time lattice that plays a really important role. But I wouldn't, but there are definitely, there might not be continuum Lagrangians that you can write down. But that's not really the definition of a field theory. I mean, I'll just throw that out there and maybe we can move on. I'm not going to try to define field theory in this talk because I'll just get myself in trouble.
Mike, could I ask you just, since the slide is up, so imagine that I start from a Hamiltonian somewhere in terms of these two parameters, G1, G2. I flow to a fixed point as defined here. Is your statement is that then if that point describes a gapped theory, then there must be a TQFT that corresponds to it?
Yeah, that's what this conventional wisdom would say.
Right.
Yeah.
But are there, well, for instance, one could ask, well, Haldane phase, you could start and you could flow to a specific point. Maybe it's representable by AKLT Hamiltonian on a lattice. But are you saying there is actually a 1 + 1 dimensional TQFT whose properties would replicate what Haldane phase is about?
Mm-hmm. Yeah, there is. Yeah.
I see. And what would that be in that specific
Well,
case?
it's yeah, I mean, the thing is, like, it's often these theories are, so usually, right, so sometimes it's not something where I can just like write down the Lagrangian very quickly and say what it is. So usually these are theories. Okay, what you need to do when you're doing TQFT is that basically a TQFT is sort of an instruction book that tells you, like, if you have a spatial manifold, it associates a quantum state. If you have a space-time manifold that evolves from one spatial manifold to another spatial manifold, it associates a linear map between quantum states. And so at the most abstract level, that's what a TQFT is. It's something you get by evaluating some functional integral, but maybe you don't necessarily need to know what the action of the functional integral looks like or how to actually do the functional integral. There are some axioms that you can require that all this satisfies. And so in that sense, there really are TQFTs that you can define, say, for the Haldane phase. You can write down, I think in the case of the Haldane phase, it depends what symmetries you're interested in, because there are a lot of different symmetries that you might care about when you're studying the Haldane chain. The probably simplest from a field theory point of view is to say that you care about two perpendicular spin rotations by pi. So that's a Z2 cross Z2 symmetry. It's kind of the minimal symmetry you need. So for that symmetry, I think you can write down something that you can write down a kind of action that has a Chern-Simons flavor. but it's, you know, but it's a little bit more abstract. But it's written in terms of basic things that you can think of as Z2 gauge fields, and there's a certain topological term that you can write, which is the only important term that goes into the action. And in order to really define it carefully, you probably have to be on a lattice. Well, if you want to write down a Lagrangian, I'm not sure that you can really make sense of that in the continuum. But you know, so there are, you know, yeah, there are actions like that. They tend to have the all these actions. Well, all these TQFTs for SPT phases, they have the flavor of response theories where what you're doing is you're coupling your system to some background gauge field, or you're putting it on space-time manifolds of different topologies or something, and you're looking at the response to that. But that's one thing, you know, that's something that you can do once you have a field theory. And so that's, you know, it's usually, the field theories are sort of that, they're all of that flavor.
Thank you.
Yeah, I mean, that's not, I mean, I don't know how satisfying that is, but it's hard to kind of do it justice in just a minute or two without writing something down. Yeah. Okay, good. Okay, so now in just the last few minutes, let me give a flavor of what's different about fracton phases. So they don't fit into this standard paradigm. And so the thing that breaks is this association between fracton phases and stable RG fixed points. So we can very explicitly understand that that doesn't work anymore. There are continuum quantum field theories that people have written down. And studying them is actually quite an active topic. But it's true that in most cases, the relationship between those field theories and the universal properties of the phases that maybe they originally come from is not very well understood. So it's not really, you know, there's the connection, you know, that we usually have is not very well understood. Do we have anything like a scaling limit theory? Well, I think there's some progress in that direction, but that's far from understood. And it's very clear that gap fracton phases are not described by TQFTs. You can see that just by observing that their ground state degeneracies get big as you increase the system size. But in a TQFT, the ground state degeneracy only depends on the topology of the space that you put your system on. Okay, so so why does this connection between phases and RG fixed points break? So this is really the key piece of work that gives us insight into this. This is some work by Wilbur Shirley, Kevin Slagle, Zhenghan Wang, and Xie Chen. So they made an interesting observation about the X cube model. So if you just take the X cube Hamiltonian, you can do entanglement RG on it, like for the toric code. And so you can take your X cube model in an L by L by L system, and you can transform it to a smaller X cube model where you cut the linear size in half. But the price of doing that is now not just a bunch of decoupled spins. It's more interesting. You wind up with a whole bunch of two-dimensional toric code layers when you try to do that. So you actually pull off all these 2D toric code layers. And the number of them in each, you have them in all three directions, and the number of them also scales with L. Okay, so what you wind up getting, you go from an X cube model in size L to an X cube model in size L over 2, and a bunch of 2D toric code layers. Now it's very tempting to say, well, great, let's just integrate out those toric code layers. We don't need them. But in a conventional RG, you're not allowed to do that because there are low energy topological excitations associated with those layers. There's some non-trivial topological phases. You're not supposed to integrate them out. Okay, and it definitely violates the rules of conventional RG. So if you want to play by conventional rules, then at this point you just have to stop and you say that, well, no RG fixed, it looks like no RG fixed point is possible. Okay, and there's something really fundamental about this. This isn't a scheme dependent thing. It's just kind of unavoidable that you're getting these extra toric code layers. But you don't have to just stop. And they did not just stop. They said, well, all right, but what if we allow ourselves to integrate out the toric code layers? Then you're just changing the rules of the RG. So, maybe you shouldn't call it RG anymore, but then you can have a fixed point, because then you'll go from the x cubed model to a smaller x cubed model. And again, in the limit of infinite size, it's like you don't change anything. So you have something like a fixed point. But the price of doing that is you have to change the rules of the RG game. And so what are the consequences of this observation? So one consequence, right? So in order to change the rules of the RG game, you have to kind of change what phase you're in, because integrating out these toric code layers actually changes what phase you're in. You're getting rid of some non-trivial topological phases, which normally you're not allowed to do. Okay, so the RG doesn't really preserve what phase you're in anymore. And so going along with that, there's no reason to expect that any continuum theory, any nice continuum theory is actually going to capture all the universal properties of the x cubed phase. And our usual notion of a quantum phase of matter still makes sense. There are still universal properties. You can still ask what property is the same everywhere when you change parameters and so on. But what's not clear is the role for quantum field theory. And so one thing you can do, which is also what the same authors did, is that you can say, well, let's just coarsen our definition of a phase. Let's say that any two states that are related by stacking on some 2D layers are in the same phase. So that will, that will give a very that will expand or coarsen our notion of what a phase is. A lot of things that used to be in different phases will be in the same phase now, but you can certainly do that. And they called that a foliated Fracton phase. Okay, and so we do expect, because of this connection to RG, that the universal properties of foliated Fracton phases are going to be captured by some continuum scaling limit QFT. But we might not know what that continuum theory is yet. There's some progress in that direction, but I think we don't really have formulations of those theories yet. But we have a reason to believe that they should exist. So if you only care about properties that are the same within some foliated Fracton phase, then there should be some nice continuum description.
And in this definition, the fixed point you get from the typical Fracton phase is different than the fixed point for just a plain stacking of toric codes or something?
Yeah, so so in this way of doing things, if you just have a plain stacking of toric codes, that's actually in the trivial phase. And that sort of shows you sort of what's weird here, right? Because, I mean, a kind of
So there's a
colorful way of putting it is this, right? Like if an experimentalist in a material actually discovered something that's in a stack of toric codes, that's like a major breakthrough. It's very non-trivial. But in this business, you have to treat that as trivial and say that it's the same thing as the trivial phase. So, you're ignoring stuff which is very non-trivial in order to get an RG fixed point. But yeah, so a stack of toric codes, that's an RG fixed point, but it's the trivial RG fixed point. It's the same as just if you had a product state of a bunch of spins. Yeah, so okay, and what this diagram is meant to show is that this kind of RG procedure doesn't respect phase boundaries anymore, right? So this black line is an ordinary phase boundary. These blue lines would be foliated phase boundaries. So this phase and this phase would be in the same foliated phase, and you can go across this boundary when you run the RG. So you get, there's some kind of association between some kind of phases and RG fixed points, but it's different than what usually happens. Okay, so that sort of, I mean, there's a lot that's not worked out there, but that sort of all sounds very promising. It sounds like there will be some, eventually there will be some parallel story for Fracton phases, which sort of mirrors what we already know. But actually, that's only true for some Fracton models. So the situation is not quite so rosy if you look more broadly. And it's much more mysterious if you look more broadly. So if you go back to this Haas cubic code model, you can also ask what happens there if you try to do entanglement RG. And that's actually something that Ha did in one of his early papers. So just schematically, what happens if you take the cubic code model in size L, it winds up becoming, and you run a step of entanglement RG, you get another cubic code, which is in half the size. And then you get something which Ha called model B, which is also defined on a lattice of half the size. But the thing about model B is it's another Fracton model, which is very similar in properties to Haas code. It's not the same as Haas code, but it's some other Haas code-like Fracton model. It's equally complicated. And if you run entanglement RG on model B, then it bifurcates. You get two model Bs in half the size. So how can you get an RG fixed point out of this? Well, the only way is if you say, let's integrate out model B. But you don't want to do that because model B is the same kind of thing that you're interested in and want to understand. So you really should not be integrating it out. So there's no justification for that if your interest is in continuum field theories. And so the thing to take away from this is that really for Haas code, there's no good reason to believe that any useful continuum description exists. I'm not saying it doesn't, but I'm saying that nobody has a good argument for that. So I'm pretty pessimistic about that. And we probably have to have a different way of thinking about its universal properties, which does not, should be something completely different from continuum quantum field theory. So, you know, on the one hand, that sounds exciting because it's new. I mean, on the other hand, I'm not sure that anybody actually has any good ideas about that. So it's also hard. But it's, you know, certainly an interesting situation. So, you know, just to summarize, there are a lot of open questions here, and some of them are easier, some of them are harder. I think one of the easier ones is trying to develop some nice continuum field theories of Fracton phases like the X-cube model. So that's, I think, doable. I think it will probably happen over a number of years. A harder question, which it will be great to grapple with, is, you know, what about the universal properties of phases like Haas code? How should we really think about them? And, you know, and it's also interesting to ask about, you know, can we learn something about other situations in condensed matter physics, perhaps non-Fermi liquids, where we might not really understand very well or completely the relationship between continuum field theories and say phases of lattice models. So, you know, fractons are sort of a good setting to think about issues like that because, you know, there are gap fracton phases, so they're not really that complicated still. It's not like a non-Fermi liquid or a conformal field theory where you have, you know, complicated strong interactions down to low energies. So maybe there's something that can eventually be learned about other kinds of problems. And something that people are definitely thinking about right now, and this actually, you know, well, there are people in the high energy community who have gotten interested in this subject, especially Nadi Seiberg and Shuheng Xiao and people collaborating with them. You know, there, I think the question is not so much what I was talking about, but rather, you know, can you get inspired by what we've learned about fractons in condensed matter physics and try to learn something interesting about quantum field theory? And I mean, that question, it should be related to the questions that I'm talking about, but it's not exactly the same question. But that's another direction that people are certainly going in this topic right now. Okay, so that's all I have. So thanks very much for listening and for your questions so far.
Fantastic. Well, on behalf of everyone, I'll clap.